All right, you crazy kids. Here's your lecture on covalent bonding. So, the most important thing about covalent bonding to remember is that it is the sharing of electron pairs, not just individual electrons, but pairs of electrons. We have some definitions for you. A molecule is a neutral group of atoms that's held together by covalent bonds. So, by definition, if you're using the word molecule, you better be talking about things that are sharing electron pairs. Ionic bonds would never form a molecule. They form formula units, totally different. A molecular compound is a compound made of many molecules. We don't really use that often, but in case you see it. And then we have a molecular formula that shows the kinds and numbers of atoms present. That's different from ionic bonds. So a molecular formula like CO2, two nonmetals, carbon and oxygen, that's literally one carbon and two oxygens. That's totally different from ionic bonding, in which we have a ratio of cations to anions. So different concept, different game, different rules. We're going to show you the formation of a covalent bond with this little drawing over here. So I have A, B, C, and D. And we have potential energy and distance. We're going to start with two atoms that do not affect each other. So they're far enough away so that their positives can't feel their negatives on the other adjacent atom. As they drift towards each other, they're going to start to be attracted by attractive forces. What I mean by that is if I have this atom over here and it goes just a little bit closer, now I'm going to have an attractive force between the positives on one atom and the negatives of the other atom. That's going to cause them to keep on getting closer and closer together. So those positives start attracting, they start getting closer, and their potential energy starts to go down. They're going to keep on getting closer and closer and closer until they get too close. So, well, let's see if I can delete this. Yep, here we go. So they're going to get closer and closer and closer until they get way too close. And if they get way too close, you can kind of already see it. The protons are going to start repelling each other, and the electrons repel each other. So that means their force of repulsion is then going to overwhelm your force of attraction, and they're going to get further apart again. And they're going to get closer again because the attractive forces outweigh the repulsive forces, and they're going to get farther apart. And they go back and forth, kind of like this, until they end at a perfect distance in which your attractive forces, seen in pink, are balanced by your repulsive forces, seen in blue. And that would be point C. So that's kind of how the bond forms. If I were to draw this in action, it would go from A to B to C to D, back to C to B to D to B, and then it would go back and forth, back and forth, back and forth. And it finally ends, like I said, when you have the lowest possible potential energy between them. And that's when your attractive forces are balanced by your repulsive forces. That's hopefully what I wanted to convey. Let's look at characteristics. So we have something called bond length, the distance between the nuclei at their minimum potential energy. On this picture up here, it would be represented in that green little portion. It's important to note that when a bond is formed, energy is released. Well, how is that possible? Well, if we remember, we started up here at high potential energy, and we're ending here at low potential energy. The difference between your start and end potential energy is the amount of energy, therefore, that is released when the bond is formed. Weird thing to think about, when dynamite explodes, a big bada boom, that's actually the formation of bonds. You're creating nitrogen triple bonds, and energy is released. That energy we see as an explosion. One of the things you got to keep in mind. We also have bond energy, the energy that's required to break a covalent bond and form isolated neutral atoms. So if I looked at this example up here, it'd be like hitting this with like an axe. That's a pretty good axe. Okay, well, that's a weird axe. Let's see if I can make it a little better. It's got like a brown handle. Here we go. It's got a red blade because it's bloody. I don't know, this is getting weird. But that would be the bond energy, okay? If I were to take this axe, that would be energy. I'd chop my molecule there, and I would be able to break the bond. So that would be bond energy, the energy required to break a bond. Shorter bonds have more energy. They're closer together because the force of attraction would be greater. You require more energy to actually break them. Longer bonds, the forces of attraction are further apart, requires less energy to break those bonds. If I have a triple or a double or a single bond, the triple bond is going to be the strongest, and then the double bond, and then the single bond. Those would all be referring to how many pairs of electrons you're sharing. As I go through this lecture, that'll make more sense, but a single bond is the sharing of one pair of electrons, total of 2. Double bond, 2 pairs of electrons, total of 4. And a triple bond, sharing of 3 pairs of electrons, a total of 6 electrons being shared. Lewis structures are how we're going to actually show what's being shared, where it's shared, and the overall shape of the molecule. So we're going to use electron dot notation to represent covalently bonded molecules. We are going to do this in a step-by-step process. I'm going to show you a very good method. You don't have to follow this method, but by golly, it kind of works. I've been doing this for a long time. Oh, I'm sorry, we missed a definition here. Unshared or lone pairs of electrons are electrons that are not involved in bonding. I'll show you what those look like in a minute. So our step-by instructions are as follows. The first thing to remember when we're building a molecule is that you're building a symmetrical molecule. In nature, things tend to be symmetrical, just one of those things. The least electronegative element goes in the middle of the thing you're going to be building. So I'm going to put something in the middle here, and I'm going to be building a molecule around it, and it's going to be a nice symmetrical molecule. All right. When I am considering my central atom, if I happen to have carbon, like my example here, here's my carbon, carbon will be the central atom. That's the very unique thing about carbon. They form what we call the backbones of molecules. If I have more than one carbon, I'll put all the carbons together and literally form a backbone. I can show you what that looks like too. The most important thing here to remember is that hydrogen never goes in the middle of your molecule that you're building. So these are Lewis structures. We're showing the shape of molecules. This is what we want to do. Next thing we got to do is determine the total number of valence electrons. So I literally add them up. Carbon has 4, hydrogen has 1, iodine has 7. In reality, I have 3 hydrogens, so I got to multiply that times 3. That gives me a total of 14 valence electrons in this example. I'm going to arrange these atoms with single bonds and then add valence electrons to complete octets. I'm not going to use more than the ones I have available. So I'm going to start with my carbon in the middle. I'm going to start bonding things to it. I'm going to show a line as a pair of electrons. So I have 4 things. I'm going to organize it nice and symmetrical. I'm going to put 3 hydrogens there and an iodine here. It doesn't matter where that is. And in fact, any rotation of this would be correct. It doesn't really matter. I could put the iodine on the top, the bottom, the left, or right. It does not matter. Mine just happens to be on the left. After I've done that, and I've arranged things with single bonds, I'm going to add valence electrons to complete octets. But I cannot add more than a total of 14 valence electrons. In these cases, or in this case, each line is equal to 2 electrons, a shared pair of electrons. So I have used a total of 8. 2, 4, 6, 8. I have how many more to go? 6. So I'm going to add those where I need them. Currently, hydrogen has an octet, 2 electrons. This hydrogen has an octet, this hydrogen has an octet, and this carbon has an octet. It has 2, 4, 6, 8 electrons around it. The only thing that doesn't have an octet is that iodine. So what I'm going to do is add electron pairs to make sure it has an octet. I've used 8 electrons. I have 6 more to go. 1, 2, 3, 4, 5, 6. Now I've completed all the octets that I need to complete. If I ran out of valence electrons, I would have to share additional pairs of electrons to complete octets. I didn't run out, so I don't have to do that. But that's what I would end up doing. When I have to do that, well, when I have to actually make double or triple bonds, I'll maybe sharing more than one pair of electrons. 2 examples are going to be CO2 and N2 to show you that function. For CO2, I got a total of how many valence electrons? I got 4 from my carbon. Each oxygen has 6. That's 12 plus 4, a total of 16 valence electrons. I'm going to put carbon in the middle and make it nice and symmetrical so it looks like that. I'm going to at least start with 1 bond. Each line represents a bond, so I've used 4 valence electrons. Now I'm going to complete octets, starting in the middle and working my way out. So carbon needs 2 more electrons on each side, so it now has an octet, 2, 4, 6, 8 electrons. I've used 8, I have 8 more to go. So 8, 9, 10, 11, 12, 13, 14, 15, 16. When I'm adding electrons, I'm going to add them symmetrically. Everything's always symmetrically. Now, looking at that, I don't have octets on my oxygens. I have it on my carbon. Maybe I'll use green. I have it on my carbon, but I do not have it on my oxygens. I only have 6 electrons there and 6 electrons there. What I do is I'm going to share additional pairs of electrons to make octets. So here's a pair from carbon that I'm going to share. I'm going to take these 2 electrons down here, and I'm going to move them right here. That doesn't change carbon's octets. It still has 2, 4, 6, and 8. However, now that oxygen on the other side has an octet, 2, 4, 6, 8. I'm not quite done because I'm going to have to add another double bond on the other side to take care of this oxygen's octet. So once again, I'm going to take these 2 electrons in the top of carbon, shown here, and move them here. Now carbon has an octet, and each one of my oxygens have octets. Another example would be N2. So I add up my total number of valence electrons. I have 10 valence electrons. I'm going to start with just 2 nitrogens bonded together. That's how it works. Now I'm going to have to add electron pairs until I get to my 10 total valence electrons. So that's 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, looking at it, it doesn't look like I have octets. I only have 6 electrons around each atom. So what I have to do is share additional pairs. I'm going to be taking electrons and creating double bonds or triple bonds as required. Let's take a look. If I take this pair here and share them in between, does that complete my octets? Well, I have 2, 4, 6, 8, so this nitrogen's good. 2, 4, 6, this nitrogen is not quite complete yet. So I need to share yet another pair of electrons. I'm going to now share this pair of electrons. So I'm going to erase those, draw those as a line between my 2 atoms, and now I can see it with a triple bond. Each atom has 8 total valence electrons. In reality, what's happening here is you're overlapping orbitals. And we can see that with our electron configuration. Here I have 2 nitrogens in their electron configuration. Here's the overlapping of px, py, and pz shown here. And that's how a triple bond actually forms. I'm going to do another video for polyatomic ions.